Section 3.2 deals with exponential functions. So the first thing we need to familiarize ourselves with, and we've put this in here for your convenience, is you need to make sure that you actually know the properties of inverses. So if you know our exponents, so if you know how exponents work, right, when we're simplifying and solving equations, we can apply these properties. And you need to know them forwards and backwards. So if you see b to the n plus m, you should know that you can split it apart. Sometimes it may be more advantageous for us to combine things and go this way. So we need to make sure we have these rules kind of down cold. But to understand what an exponential function is, let's compare it to a power function. So a power function is a variable raised to a power, like y equals x squared. The variable's in the base. An exponential function is a constant base raised to a variable power, like 2 to the x. So the variable is in the exponent. The general form of an exponential function is y equals b to the x, where b is the base of the function, and b cannot equal 1. Because if b is 1, then anything 1 raised to any power is just going to return 1 back. You would just have a horizontal line. If b is between 0 and 1, the function will decrease. And if b is greater than 1, the function will increase. So let's look at what's happening here. So this is the general form. So if x is 0, any number raised to the 0 power is 1. So this graph, on both cases we're going to look at, is going to pass through the point 0, 1. So if we want to look at the first case, where b is between 0 and 1, the function will get smaller and smaller because you're just taking a fraction and multiplying it by itself over and over again. So you can kind of think of like 1/2 to the x. Every time you use plug in the next value of x, you're cutting the previous answer in half. So it's just reducing and reducing. So its y-intercept is 0, 1, and we can see it's decreasing over time. However, if b is greater than 1, b to the 0 is still 1, but now it's going to increase exponentially. So if we think of 2 to the x, well, every time you raise your power by one more value of x, you're doubling your previous answer. So it's going to behave in the exact opposite way. So this, right, is 0, 1. And so both of these are the function y equals b to the x graphed, but it shows what the value of b does to the graph. So let's look at example 4. So example 4 says solve for x. So the first thing that you want to do when you're solving these, before you just dive in, and we're going to see in a little bit we can actually use logs to be the inverse, but there's a really cool property up here that a lot of people don't pay attention to, and it's kind of my favorite one, right? And it's actually not listed because it's not really an algebra property, okay? But if you notice what's happening here, we have a b, 27, raised to a power, and a b of 81 raised to a power. So these are two different bases. There's a really cool property that says if you have a base raised to some expression, right, and it's equal to the exact same base raised to a different expression, as long as b is not 1, then the exponents have to equal each other. So the one thing that I always check for before I solve a problem, because this thing makes life super easy, is look at those two bases, 27 and 81. Do they have anything in common? Because if I can rewrite this equation in this form, all I have to do is set their exponents equal to each other. So in this case, I see 27, which is divisible by 3. 81 is divisible by 3. Now some of you might say, oh, they're both divisible by 9. Well, that's true. 27 is 3 times 9, right? 81 is 9 times 9. And remember, the goal is to find the smallest possible base. So it's always helpful to check your primes, right? Check 2, check 3, because we want to see if we can reduce it to some number raised to a power. So 27 is actually 3 cubed. And all of that is raised to the 3x plus 2. 81 is 3 to the 4th. And that's all raised to the 4x plus 5. So going back to my properties, if I look back up here, if I have a power raised to another power, you multiply the two exponents together. So if I come back down here, because I'm still not quite in this form yet, 3, so I distribute this 3 across the expression. So now I get 9x plus 6, and here I distribute the 4 across. So I get 16x plus 20. And now I'm where I want to be. So I have b raised to some stuff equals the same b raised to different stuff. So that means that these two expressions have to be equal to each other. So I can subtract a 9x from both sides, and I get 7x, and I can subtract a 20 from both sides, and I'll get negative 14. And now when I divide by 7, I get that x equals negative 2.